When you picture Saturn, what's the first thing that comes to mind? For most of us, it's not just a giant swirling ball of gas and liquid hydrogen, though that in itself is remarkable. No, it's that magnificent, iconic halo. Those impossibly delicate yet immense rings that cut across the blackness of space like a celestial adornment, a shimmering disk of cosmic jewelry. From the moment Galileo first peered through his crude telescope in 1610 and saw what he described as Saturn's ears, to Christian Huygens' definitive observation 50 years later that they were indeed rings, humanity has been utterly captivated by this planet's unique feature. They are, without a doubt, the solar system's most recognizable accessory, a testament to cosmic beauty and grandeur, adorning countless textbooks, sci-fi films, and artistic renditions of our solar neighborhood. These rings aren't merely beautiful. They are a profound visual anchor. They define Saturn. They are its cosmic fingerprint, distinguishing it from all other planets. They imbue it with a sense of eternal grace and unyielding permanence. We look at them and we subconsciously assume they've always been there, encircling their majestic parent planet for billions of years, and that they will remain for eons to come. They feel like they're set in stone, or rather, in Isan, an unchanging fixture in the vast, dynamic cosmos. But what if I told you that this deep-seated belief, this perception of eternal grandeur, is fundamentally, profoundly, and quite surprisingly wrong? Imagine for a moment gazing at a magnificent ice sculpture, intricately carved, catching the light in 1,000 dazzling ways. You admire its artistry, its fleeting beauty. But what if, instead of slowly melting away over hours, this sculpture was actively raining its own material down into the pedestal it stands on, day after day, year after year? That, in essence, is what's happening to Saturn's rings. This is the perplexing paradox at the heart of our journey today. These seemingly everlasting, sparkling structures, the very emblem of cosmic stability, are actively, measurably, and irrevocably disappearing. They are fading. Right now. For centuries, astronomers simply assumed the rings were as old as Saturn itself, formed alongside the planet 4-5 billion years ago from the swirling dust and gas of the early solar system. Why wouldn't they be? They certainly look ancient, weathered by the eons, yet perfectly maintained in their elegant dance. But the universe, as we're learning, is far more dynamic and surprising than our initial assumptions. According to groundbreaking research, particularly the extraordinary data gathered by the Cassini spacecraft during its final, daring dives between the rings and Saturn itself, this iconic spectacle is on a cosmic countdown. Scientists have found compelling evidence that Saturn's rings are losing mass at an astonishing rate. We're talking about tons of material, every single second, literally raining down into Saturn's upper atmosphere. This phenomenon has even been given a name, ring rain. Think about that for a moment. This isn't some theoretical, distant future event. This is happening as we speak. Icy particles, some as tiny as smoke and others as large as boulders, are being pulled from the rings, vaporized, ionized by ultraviolet light, and then drawn in by Saturn's powerful magnetic field, plunging into the planet below. It's a slow, steady, continuous drain. This isn't just a trickle, it's a measurable deluge. To put it in perspective, according to some models based on Cassini data, the amount of water ice falling into Saturn's atmosphere from the rings is enough to fill an Olympic-sized swimming pool every half hour. Now, picture that happening for millions of years. It paints a vivid, almost heartbreaking picture of a slow-motion cosmic erosion. So, if the rings are disappearing, how quickly are they vanishing? And what does that mean for their ultimate fate? Well, while an Olympic swimming pool every half hour might sound like a lot, the rings are enormously massive. But even with their incredible scale, according to recent estimates, Saturn's iconic rings may only have another 100 to 300 million years left before they are largely gone. 100 to 300 million years. That might sound like an eternity to us, but in the context of the solar system's 4.5 billion year history, it's barely a blink. It means that the rings we see today are, cosmically speaking, a relatively recent and incredibly transient phenomenon. This discovery flips our understanding of Saturn on its head. It transforms our view of this seemingly permanent fixture into something profoundly ephemeral, a beautiful fleeting adornment on a cosmic timescale. It forces us to ask a whole new set of questions. How did scientists even figure this out? What exactly is a ring ring, and what other forces are at play in this cosmic dissolution? If the rings are so young, where did they come from in the first place? What was Saturn like before they appeared, and what will it look like when they're gone? How will this profound change affect Saturn's moons, which have evolved in their gravitational embrace? And ultimately, what do these magnificent disappearing rings teach us about the dynamic, surprisingly fragile nature of planetary systems throughout the universe? Join me as we embark on a journey of discovery, unraveling the surprising science behind the end of the rings. We'll delve into the astounding data, explore common misconceptions, meet the leading theories, and ultimately arrive at a counterintuitive conclusion that reshapes our appreciation for one of the solar system's most beloved wonders. The countdown has begun, and the universe is ready to reveal its secrets. Last time, we opened with a bombshell. Saturn's magnificent rings, those seemingly eternal cosmic wonders, are actually disappearing. They're on a countdown, slowly but surely raining down into the planet below. But to truly understand how they're disappearing, and why this is such a profound discovery, we first need to get up close and personal. We need to ask, what exactly is Saturn's rings made of? If you were to look at a high-resolution image of Saturn, especially from afar, the rings often appear like a solid, continuous structure, a vast, glowing disk. Perhaps you imagine them as giant, pristine sheets of ice, or maybe even some sort of solid, exotic material. It's a common mental image, and it's perfectly understandable. After all, they appear so uniform, so smoothly curved. But the reality, as is often the case in science, is far more intricate, more surprising, and infinitely more dynamic than our initial perceptions. Not even close. If you could somehow fly a spacecraft directly through them, which, by the way, NASA's Cassini probe did in its final, daring act, you wouldn't encounter a solid barrier. Instead, you'd find yourself immersed in a cosmic blizzard, an impossibly vast, swirling throng of countless individual pieces. Imagine a colossal cosmic demolition site, but instead of debris settling, it's perpetually orbiting. Saturn's rings are made up of billions, possibly even trillions, of icy particles. Think of it like a giant, decentralized moon, shattered into an unimaginable number of fragments, each now orbiting Saturn independently, yet collectively creating the illusion of a solid structure. What kind of ice are we talking about? Primarily, water ice. Yes, the same stuff that makes up the ice cubes in your freezer, or the snow that falls in winter. But here, in the cold vacuum of space, far from the sun's warming embrace, it exists in a state of stunning purity. According to spectroscopic analysis from missions like Voyager and Cassini, these icy particles are incredibly clean, almost 99% pure water ice, with just a tiny smattering of rocky material and carbonaceous compounds. This purity is a crucial clue, as we'll see later, to understanding their surprisingly young age. Now, let's talk about size. The particles aren't all uniform, like grains of sand on a beach. Oh no, it's a wild mix. At the smallest end of the spectrum, you have micron-sized dust particles, so fine they're almost like smoke. These are essentially microscopic ice crystals, catching and scattering sunlight to give the rings their shimmering brilliance. They're so light that they're highly susceptible to external forces, like solar radiation pressure and electromagnetic fields, which plays a big role in their disappearance. Then, you have the more substantial chunks, pebbles, gravel, even rocks the size of boulders. If you could reach out and grab a handful, you might hold a collection ranging from something smaller than a grain of rice to something that could easily fit in your hand, or even larger. But it doesn't stop there. Some of these icy fragments are truly gargantuan. We're talking about chunks as big as houses or even small mountains, several tens of meters across. Imagine flying past an ice mountain, tumbling slowly through space, part of this colossal, intricate dance. These larger objects are less affected by things like solar wind, but they still play a crucial role in the ring's internal dynamics and evolution. So, when you see a bright, wide ring, like the A-ring, it's not just one unbroken band. It's a dense, crowded highway, where icy particles of all shapes and sizes are orbiting Saturn, each at its own specific speed, constantly interacting with its neighbors. The sheer number of these particles is mind-boggling. If you could somehow gather all the material in Saturn's rings, according to calculations based on their total mass, you might end up with something roughly the size of a small moon, perhaps 300 to 500 kilometers across, like one of Saturn's mid-sized satellites. But instead of being consolidated, it's spread out into this unimaginably vast cosmic disk. And how vast is this disk? Saturn's main rings span an astounding 200,000 kilometers, or about 105,000 miles, from edge to edge. To give you a sense of scale, that's roughly 3/4 of the distance between the Earth and the Moon. Or, to put it another way, you could fit about 22 Earths side by side across the width of the rings. It's an absolutely colossal structure, visible even from Earth with a decent telescope, a testament to its immense scale. But here's where it gets truly counterintuitive, and frankly, astonishing. Despite their incredible width, the rings are unbelievably thin. How thin? Well, if you could shrink the entire ring system down to the size of a football field, or even the distance from New York to Los Angeles, their thickness would be no more than a sheet of paper. Yes, a sheet of paper. In some places, like the main A, B and C rings, the thickness is estimated to be only about 10 to 100 meters, which is roughly 30 to 300 feet. That's thinner than a tall building, or even an average city block. In other words, for something that stretches almost the entire distance from Earth to the Moon, its vertical dimension is virtually non-existent. Well, for a long time, the exact thickness was debated, but missions like Voyager, and especially Cassini, gave us unprecedented views. Cassini, during its long orbit, performed incredible maneuvers, peering at the rings from various angles, even looking back at them as they were backlit by the sun. It observed the shadows the rings cast on Saturn, and, crucially, it used a technique called stellar occultation. As a star passed behind the rings, Cassini could measure precisely how its light was dimmed and scattered, providing incredibly detailed information about the ring's density and vertical structure. Scientists also used radio science, sending radio signals through the rings and analyzing how they were affected, providing further insights into their particle distribution and vertical extent. This extreme thinness isn't just a fascinating fact. It's a testament to the powerful gravitational forces at play, forcing these trillions of particles into an incredibly flat plane. It also means that even though there are billions of particles, they're spread so wide that they only rarely collide directly. When they do, it's usually a gentle, glancing blow, like billiard balls in slow motion, gradually exchanging energy and subtly shifting their orbits. These collisions are actually crucial for keeping the rings so flat and well-behaved, preventing them from scattering chaotically. So, when we talk about Saturn's rings disappearing, it's not some solid structure crumbling. It's an erosion of billions of individual icy grains and boulders. It's a vast dynamic system, held together by gravity, but slowly being pulled apart by other forces. Understanding this granular, icy, incredibly thin, yet immensely wide nature of the rings is absolutely essential to grasping the mechanisms of their cosmic countdown. And it leads us to our next crucial question. If these magnificent, fragile structures are actively shrinking, what exactly are the processes that cause these billions of icy particles to leave their elegant orbits and plunge into the gas giant below? How exactly does this ring rain occur, and what other factors are contributing to this monumental cosmic vanishing act? We've established that Saturn's rings are not a solid, continuous structure, but rather an intricate cosmic dance of billions of icy particles. We also know they're on a cosmic countdown, slowly vanishing. This already challenges our casual perception of them. But to truly appreciate the dynamic and fragile reality of these rings, we need to confront some other deeply ingrained misconceptions. It's time to peel back the layers of popular imagination and replace them with the startling truths unveiled by decades of scientific inquiry. The first, and perhaps most common, misconception we've already touched upon, but it bears repeating because its implications are so vast, the idea that the rings are solid. We touched on this in our last segment, but it's such a pervasive visual illusion that it's worth reiterating and expanding on. When you look at a photograph of Saturn, or even through a telescope, the rings appear smooth, uniform, and almost painted onto the planet. It's easy to imagine them as a gigantic, flat CD, or a vinyl record, perhaps with grooves, but fundamentally a single, cohesive unit. This couldn't be further from the truth. As we discussed, they are an incredibly diffuse, sparsely populated region of space, bustling with individual icy particles, each on its own orbital path around Saturn. Think of it this way. Imagine standing on a highway overpass at night, looking down at the blur of car headlights and taillights. From a distance, it looks like a continuous stream of light, but you know that stream is made up of thousands of individual vehicles, each separated by space, each moving independently. Saturn's rings are like that highway, but on a scale that defies comprehension, and with particles ranging from dust motes to mountains. The illusion of solidity comes from the sheer number of these particles, and the incredible distance from which we view them. If you were actually in the rings, you wouldn't see a solid wall of ice. You'd see a glittering, diffuse cloud of icy bits, possibly with vast stretches of emptiness between them, but with a surprising density when viewed from afar. Another major misconception is their age. For a very long time, the prevailing scientific consensus, and certainly the popular belief, was that Saturn's rings were primordial. That meant they formed at the same time as Saturn itself, roughly 4.5 billion years ago, when the solar system was just coalescing from a swirling cloud of gas and dust. It seemed logical, didn't it? If they'd been there as long as we've known about Saturn, and they look so vast and well established, why wouldn't they be ancient? This idea of ancient primordial rings suggested they were a stable, fundamental feature of the planet, essentially eternal. But as we'll explore in more detail, this notion has been completely upended by modern observations. According to a wealth of data, particularly from the Cassini mission, the rings are, surprisingly, incredibly young. We're talking hundreds of millions of years old, at most. Maybe even less than 100 million years. That's a baby in cosmic terms. To put that into perspective, when dinosaurs roamed the Earth, Saturn might not have even had its rings yet. Humanity, as we know it, is a fleeting blink in the ring's estimated lifespan. This revelation is a complete paradigm shift, transforming the rings from an ancient static relic into a dynamic, transient phenomenon, a cosmic recent event that we are privileged to witness. This youthfulness is a critical piece of the puzzle, and it's something we'll dive deep into later. Then there's the idea that the rings are static, unchanging structures. The beautiful concentric circles seem so perfectly drawn, so stable. It's easy to picture them as a fixed, unmoving sculpture in space, but this, too, is far from the truth. Saturn's rings are an incredibly dynamic environment, a constant ballet of motion and interaction. First, consider the individual particles. Each one is orbiting Saturn at its own speed, according to Kepler's laws of planetary motion. Particles closer to Saturn orbit faster than particles further out. This means there's a constant differential motion, a shearing effect between adjacent particles. It's like a racetrack where the inner lanes are moving faster than the outer ones, but everyone is constantly passing each other. This differential motion, combined with the sheer number of particles, leads to constant, albeit gentle, collisions. Imagine billions of microscopic ice, billiard balls constantly bumping into each other. According to scientists studying ring dynamics, these collisions are not violent, destructive impacts. Instead, they're more like soft encounters, gentle nudges that redistribute energy and keep the ring particles in their incredibly thin, flat plane. They're what prevent the rings from becoming a thick, fuzzy donut. These continuous interactions are what maintain the ring's complex structure, creating the numerous distinct rings and gaps we observe. And it's not just internal dynamics. The rings are also constantly interacting with Saturn's many moons. We're not talking about just the big ones like Titan or Enceladus, but also the smaller shepherd moons that orbit within or near the rings. These tiny moons exert gravitational forces that sculpt the rings, creating the sharp edges of the A and B rings, carving out the Cassini division and generating fascinating ripple patterns and density waves that propagate through the ring material. It's like a cosmic choreographer, constantly shaping the dance. Furthermore, the rings aren't just orbiting in a perfectly flat plane forever, they exhibit seasonal changes. As Saturn orbits the Sun over its long 29.5-year year, the angle at which the Sun illuminates the rings changes. This causes variations in the shadows cast on the planet and within the rings themselves. We even see transient spokes, mysterious dark, radial markings that appear and disappear as the rings rotate. These features are still not fully understood, but scientists believe they are caused by electrostatic forces lifting fine dust particles out of the ring plane. This is another clear indicator of their dynamic and constantly evolving nature. So, when we consider these factors, the rings are not solid, they are surprisingly young, and they are incredibly dynamic. They are not ancient, static monuments. They are fleeting, vibrant, and incredibly active systems, subject to constant change and, ultimately, a finite lifespan. This new perspective doesn't diminish their beauty. If anything, it enhances it. Knowing that we are witnessing a relatively brief, magnificent phase in Saturn's history makes them even more precious, more profound. It turns them into a cosmic clock, ticking down, reminding us of the ceaseless evolution of the universe. In the next segment, we'll dive into the concrete evidence that underpins these revelations, focusing on the primary mechanism driving the ring's disappearance, ring rain. We'll explore how space probes, particularly Cassini, gathered the irrefutable data that allowed scientists to finally measure this cosmic drain and truly grasp the fragile reality of Saturn's iconic halo. We've stripped away the illusions. We now know Saturn's rings aren't solid, they're not ancient, and they're certainly not static. They are a dynamic, fragile, and remarkably young collection of billions of icy particles, already on a cosmic timer. This raises the most pressing question. If they're disappearing, how exactly is it happening? What's the primary mechanism behind this unseen drain, this slow erosion of a planetary icon? The answer lies in a phenomenon dubbed ring rain. It's a poetic term for a complex process, one that speaks volumes about the intricate interplay between gravity, magnetism, and the environment of space. The concept of ring rain isn't entirely new. Scientists first theorized its existence decades ago. But it took the incredible, up-close observations from our robotic envoys to truly confirm and quantify it. Our story begins in the late 1970s and early 1980s with the groundbreaking Voyager missions. These intrepid probes, Voyager 1 and Voyager 2, were humanity's first close-up reconnaissance of the outer solar system. When Voyager 1 flew past Saturn in 1980, it sent back astounding images, forever changing our perception of the ringed planet. But beyond the stunning visuals, Voyager carried instruments designed to probe the invisible forces at play. One of Voyager's key discoveries was detecting strange variations in Saturn's ionosphere, the upper layer of its atmosphere, filled with charged particles. Specifically, instruments detected charged water molecules, which seemed to be arriving from somewhere beyond the atmosphere. Now, water in Saturn's atmosphere isn't entirely unexpected. It's a gas giant after all, with a complex chemistry. But these observations hinted at something unusual, something external. Scientists at the time, like Jack Conany, proposed that these charged water particles were originating in the rings and being funneled into the planet's atmosphere by its magnetic field. It was an intriguing hypothesis, a theoretical ring rain, but direct, undeniable proof remained elusive. Voyager simply couldn't get close enough to see the process in action. Fast forward to 2004, and the arrival of the Cassini-Huygens mission at Saturn. This was a game-changer. Cassini wasn't just a flyby, it was an orbiter, designed for a marathon study of the Saturnian system that lasted an astonishing 13 years. Cassini was equipped with a suite of sophisticated instruments, including a plasma spectrometer, an ultraviolet imaging spectrograph, and a radio and plasma wave science instrument, all geared to sniff out the subtle signatures of ring material. According to a series of papers published in the mid-2010s, utilizing Cassini's extensive data, the process of ring rain was not only confirmed, but meticulously detailed. Here's how it works. Imagine those billions of icy particles in the rings. They're constantly exposed to a harsh environment. The primary culprit for initiating the rain is ultraviolet, UV, light from the sun, and to a lesser extent, meteoroid impacts and charged particles from Saturn's magnetosphere. When UV light hits these tiny icy particles, especially the smaller, dustier ones, it strips electrons away from the water molecules, causing them to become electrically charged or ionized. Think of it like static electricity, but on a cosmic scale. These newly charged water molecules, along with tiny bits of ice, now possess a positive charge. But Saturn isn't just a gas giant with rings. It's a giant magnet. Like Earth, it has a powerful magnetic field that extends far into space, encompassing its rings and many of its moons. This magnetic field acts like an invisible force field, guiding any charged particles that venture into its domain. Once these ring particles become ionized, they are no longer just subject to Saturn's gravity. They also become slaves to its magnetic field. The magnetic field grabs these charged water particles and begins to pull them along its field lines. Think of the magnetic field lines as invisible tracks radiating out from Saturn's poles, looping back into the planet. These ionized water particles, now caught in the magnetic grip, are essentially funneled along these tracks, drawn inexorably towards Saturn's upper atmosphere. As these particles, still containing water ice, travel along the magnetic field lines, they begin to vaporize. Some of this happens due to the slight warming from the distant sun, but much of it happens as they encounter Saturn's tenuous upper atmosphere. It's like a tiny ice cube entering a warm room. It begins to sublimate directly into vapor. This water vapor, still ionized, then rains down, literally, into Saturn's ionosphere. Cassini provided direct evidence of this phenomenon in several ways. Its instruments, particularly the ion and neutral mass spectrometer, INMSS, actually tasted the atmosphere. During its grand finale phase in 2017, Cassini performed 22 daring dives through the narrow gap between the rings and Saturn's cloud tops. This was an unprecedented journey, taking the probe into a region never before explored, and what it found was astonishing. According to research published in Science in 2018, as Cassini plunged through this gap, its instruments detected an incredibly strong stream of complex organic molecules raining down from the innermost D-ring into Saturn's atmosphere. Even more strikingly, it found direct evidence of water ice and other materials like methane, ammonia, and carbon dioxide raining into the planet from the C and B rings. These weren't just theoretical particles, they were measured directly, confirming the long-held hypothesis of ring rain. One of the most compelling pieces of evidence came from Cassini's observations of dark lanes in Saturn's ionosphere. These lanes, detected in the ultraviolet, corresponded precisely to the magnetic field lines that connected directly to the rings. Scientists, led by James O'Donoghue, interpreted these dark lanes as regions where water and other material from the rings were interacting with and dampening the glow of the ionosphere. It was like seeing the direct pathway of the ring rain. These observations allowed scientists to not just confirm the process, but to measure the rate at which it was occurring. And the numbers are staggering. According to these studies, the amount of ring material raining into Saturn's atmosphere is significant. Current estimates suggest that about 10,000 kilograms of water ice and other materials are falling onto Saturn every second. To give you a relatable analogy, that's enough material to fill an Olympic-sized swimming pool every half hour. Or, if you prefer, it's roughly the mass of an average passenger bus every minute. This isn't a trickle, it's a constant, measurable cosmic downpour. And it's not just a localized event, it's happening all around Saturn, wherever the magnetic field lines connect to the innermost parts of the rings. What are the implications of this constant drain? If 10,000 kilograms of material are disappearing every second, how long can the rings last? Well, when you extrapolate that rate over vast geological timescales, the answer becomes stark, not forever. Based on these measured rates of ring rain, and considering other factors of erosion, scientists have calculated that Saturn's magnificent rings have a finite lifespan. As we touched on earlier, current estimates suggest they could largely vanish in as little as 100 million years, and certainly no more than 300 million years. This revelation, born from decades of theory and finally confirmed by Cassini's unparalleled mission, fundamentally reshapes our understanding of Saturn. It tells us that the rings are not a permanent fixture, but a transient, ephemeral beauty, a stage in Saturn's ongoing planetary evolution. We are, in effect, living in a golden age of Saturn, witnessing its most spectacular display before it slowly, inexorably fades away. But ring rain isn't the only way the rings are losing material. It's a major contributor, yes, but there are other, more subtle forces at play, slowly chipping away at this cosmic masterpiece. In our next segment, we'll explore these additional mechanisms of erosion and impacts and see how they, too, contribute to the accelerating countdown of Saturn's iconic rings. We've already uncovered the primary driver of the rings' disappearance, the astonishing phenomenon of ring rain, where charged icy particles are magnetically funneled into Saturn's atmosphere. It's a compelling, measurable drain, but the universe is rarely so simple as to rely on just one mechanism. The grand spectacle of Saturn's rings is under assault from multiple angles, a relentless cosmic weathering that complements the slow deluge of ring rain. So, what are these other insidious forces at play, slowly but surely contributing to the ring's eventual demise? Imagine a colossal, intricate sandcastle built on a beach. The tide is slowly coming in, eroding the base. That's our ring rain. But simultaneously, tiny grains of sand are being picked up by the wind. Small waves are lapping at the edges, and perhaps even curious seagulls are pecking at it. These are the additional forces working on Saturn's rings. One of the most significant, though often underestimated, factors is micrometeoroid bombardment. Our solar system is not an empty void. It's filled with an immense amount of cosmic dust and tiny rocks, remnants from the formation of planets, comets, and asteroids. These micrometeoroids are constantly zipping around at incredibly high speeds, typically tens of kilometers per second. Now, picture Saturn's rings as an enormous, flattened target. Billions of icy particles spread over a vast area. Even though the rings are thin, they present a huge cross-section to the relentless hail of micrometeoroids. According to decades of research, confirmed by instrument readings from probes like Voyager and Cassini, these tiny cosmic projectiles are constantly slamming into the ring particles. What happens when a micrometeoroid hits an icy particle? It's not like a gentle tap. At such immense velocities, even a tiny speck of dust can pack a significant punch. The impact causes a miniature explosion, vaporizing and chipping off fragments of the icy ring particle. These fragments can then either become part of the general ring population, often as even smaller dust, or they can be ejected from the ring system entirely. Sometimes they are thrown up out of the thin ring plane, where they are more susceptible to other forces. Think of it like an endless cosmic sandblasting. Over millions of years, this constant bombardment acts like a slow, deliberate grinder, pulverizing and eroding the ring material. It doesn't happen all at once, but cumulatively, the loss of mass from these impacts is substantial. Scientists have analyzed the flux of micrometeoroids in the outer solar system and estimated that this constant erosion contributes significantly to the ring's overall mass loss, adding to the impact of ring rain. Another crucial factor, one that might seem counterintuitive given the ring's thinness, is internal collisions between the ring particles themselves. We discussed how the rings are made of billions of individual ice chunks, each orbiting at its own speed. Particles closer to Saturn move faster than those further out. This differential rotation means that adjacent particles are always moving past each other at slightly different velocities. Imagine an incredibly crowded highway, where every car is moving at slightly different speeds, constantly overtaking or being overtaken. In Saturn's rings, these are usually low-velocity, glancing blows. They're more like gentle bumper car nudges than head-on crashes. But even these soft collisions have profound effects. When two icy particles collide, several things can happen. They might gently bounce off each other, exchanging a bit of momentum. They might also stick together temporarily, forming larger aggregates, which can then be broken apart by subsequent collisions. But critically, these collisions can also chip off smaller fragments from the main particles. These tiny fragments, often micron-sized dust, are now incredibly susceptible to other forces. They can be easily picked up by Saturn's magnetic field and guided into the ring rain process. They can also be pushed by the faint pressure of sunlight, or even by Saturn's extended atmosphere, gradually drifting out of the main ring system or being funneled towards the planet. So, while these internal collisions help to keep the rings incredibly flat and organized, they also act as a pulverizing mechanism, constantly creating new, smaller particles that are more easily lost. It's a self-eroding system, a cosmic feedback loop, where the very interactions that maintain its structure also contribute to its slow dissipation. Beyond these mechanical processes, we also have the subtle but persistent influence of solar radiation and the solar wind. The sun, while distant, is a powerful force. Its constant stream of charged particles, the solar wind, and its relentless output of electromagnetic radiation, including ultraviolet light, interact with the ring particles. When solar wind particles strike the icy ring material, they can knock off atoms and molecules, a process known as sputtering. This is similar to sandblasting, but on an atomic level. Ultraviolet radiation, as we mentioned in the context of ring rain, can ionize water molecules, giving them a charge and making them susceptible to Saturn's magnetic field. But it can also cause the ice to slowly sublimate directly into space, even without magnetic capture, especially for the smallest particles in the outermost, less dense rings. Think of it like leaving an ice cube out on a dry, sunny day. Even if it doesn't melt, it will slowly shrink as ice molecules turn directly into water vapor, disappearing into the air. In the vacuum of space, this sublimation is an even more efficient process, slowly but surely eating away at the icy particles, especially those on the surface of larger chunks. The combined effect of micrometeoroid impacts, internal collisions creating smaller, more vulnerable particles, and the eroding power of solar radiation and solar wind forms a multi-pronged assault on Saturn's rings. Each mechanism, individually, contributes to the gradual loss of mass. But together, they create a comprehensive picture of a ring system that is under constant, relentless attack from its environment. It's not a violent, sudden destruction, but a slow, persistent weathering, like a majestic mountain range being eroded by wind and water over geological epochs. Saturn's rings are slowly succumbing to the forces of their cosmic environment. This understanding of multiple degradation pathways reinforces the idea that the rings are not only ephemeral, but actively shrinking, their days truly numbered on a cosmic scale. This complexity, multiple mechanisms, each playing a role, is a hallmark of scientific discovery. It's rarely one simple answer. Instead, it's a mosaic of interconnected processes, each contributing to the grand, unfolding narrative. And this narrative, the story of the disappearing rings, is far from over. Because if they're so actively eroding, and if they're losing so much mass, it raises an even more profound question. Where did they come from in the first place? That's a question that completely upended decades of astronomical assumptions, leading us to the surprisingly young age of Saturn's rings, which we'll explore next. We've seen how Saturn's rings are not solid, not static, and certainly not eternal. We've explored the active mechanisms like ring rain and micrometeoroid bombardment that are systematically eroding them. This constant loss of material leads directly to one of the most astonishing and counterintuitive discoveries about Saturn's iconic feature, its surprisingly youthful age. For centuries, astronomers simply assumed the rings were as old as Saturn itself. It was a logical, almost default assumption. Our solar system formed about 4.5 billion years ago. Planets coalesced, moons formed, and the debris from this cosmic construction settled into stable orbits. So, it made sense that if Saturn had rings, they must have formed concurrently, ancient relics of the solar system's birth. This view of primordial rings was the dominant paradigm for decades. But what if the most prominent feature of the solar system's second largest planet is, in fact, a cosmic baby, a relative newcomer to the celestial stage? That's exactly what decades of scientific investigation, culminating in the unprecedented data from the Cassini mission, has revealed. Saturn's rings are not billions of years old. According to the overwhelming scientific evidence, they are, at most, a few 100 million years old. Some estimates even put their age as low as 10 to 100 million years. This is a monumental shift in understanding. It means that for much of Saturn's 4.5 billion year history, it likely existed without its magnificent halo. Imagine that for a moment, a ringless Saturn. It's a profound thought that fundamentally alters our perception of this familiar gas giant. So, how did scientists arrive at such a startling conclusion? What evidence was so compelling that it overturned centuries of conventional wisdom? It boils down to several key lines of inquiry, primarily spearheaded by the Cassini spacecraft. The first crucial piece of evidence comes from the ring's composition, specifically their astounding purity. As we discussed, Saturn's rings are almost 99.9% pure water ice. They are bright, reflective, and remarkably clean. Now, in the harsh environment of space, nothing stays pristine forever. Over billions of years, cosmic dust, micrometeoroids, and even material from passing comets and asteroids would accumulate on the rings. This constant bombardment would deposit darker, rocky, carbonaceous material onto the icy particles, slowly but surely contaminating them, making them appear darker and less reflective. Think of it like snow. Freshly fallen snow is brilliant white, but over time, as dust and soot settle on it, it turns grey and dirty. If Saturn's rings were truly primordial, 4.5 billion years old, they should be significantly dirtier, much darker, and less reflective than they are. The fact that they are so remarkably pristine, so dazzlingly bright, suggests they haven't been exposed to the cosmic environment for nearly as long as the age of the solar system. Scientists have calculated the rate at which cosmic dust accumulates on ring particles and concluded that the current level of contamination is consistent with an age of only tens to hundreds of millions of years. The second powerful line of evidence comes from the mass of the rings. Cassini, through incredibly precise gravitational measurements, was able to weigh the rings with unprecedented accuracy. By tracking its trajectory and tiny wobbles as it orbited Saturn, scientists could infer the gravitational pull of the rings and thus their total mass. According to research published in journals like Science IC and Icarus by the Cassini team, the total mass of the rings is approximately 1.5 × 10^10 kilograms. Now, that sounds like a lot, and it is, but it's significantly less massive than if the rings had existed for billions of years. Given the measured rate of ring loss through ring rain and other erosion mechanisms we just discussed, scientists can essentially run the clock backward. If the rings are losing material at this rate, and they have this much mass now, then they couldn't have lasted for billions of years. If they were 4.5 billion years old, they would have either completely dissipated by now, or they would have had to be impossibly massive at their formation, far more massive than anything we observe. The current mass, combined with the observed loss rates, strongly points to a much younger origin. A third piece of the puzzle involves the ring's dynamics and structure. The rings are not perfectly smooth. They exhibit a complex array of ripples, waves, and strange vertically undulating features. These are not static patterns, they change and evolve. According to research by Matt Tiscarino and others on the Cassini team, some of these wave patterns, particularly those caused by gravitational interactions with Saturn's moons, act like fossil records. By analyzing the precise shapes and locations of these waves, scientists can sometimes deduce the timing of the events that created them. For instance, specific gravitational disturbances would imprint unique patterns, and by modeling their propagation, researchers can estimate when those disturbances occurred. The existence of certain wave patterns and the absence of others are consistent with a relatively young system, still dynamically settling and evolving. Perhaps one of the most exciting and somewhat controversial pieces of evidence emerged from the final dramatic dives of the Cassini spacecraft during its grand finale. As Cassini plunged between the innermost rings and Saturn's atmosphere, its instruments directly sampled the material in that crucial gap. What it found was a surprisingly low density of dust and debris in this region. If the rings were primordial, this region should be teeming with fine particles accumulated over billions of years. The relative cleanliness of the ring planet gap further supports a younger age, suggesting there hasn't been enough time for a vast amount of ancient dirty material to collect there. The collective weight of this evidence, the rings' pristine icy composition, their measured mass, their dynamic features, and the relative cleanliness of the ring planet gap, paints a consistent and compelling picture. Saturn's rings are a recent addition to the solar system, a cosmic phenomenon that appeared long after the planets themselves were formed. This discovery is more than just a scientific detail. It fundamentally changes our perception of planetary evolution. It suggests that ring systems, even magnificent ones like Saturn's, are not necessarily stable, long-lived features. They can form relatively late in a planet's history, exist for a cosmic blink of an eye, and then dissipate. It transforms them from ancient relics into fleeting, beautiful phenomena, caught in a dramatic, relatively brief stage of their existence. So, if they aren't primordial, if they are indeed so young, this immediately leads us to the next profound question. If Saturn didn't always have its rings, how did they form? What cataclysmic event, perhaps in the last few 100 million years, could have created such an immense and spectacular structure? The answer involves shattered moons and the irresistible force of gravity, taking us into the heart of competing theories about the birth story of these magnificent yet ephemeral rings. That's what we'll explore in our next segment. We've established that Saturn's rings are not ancient relics from the dawn of the solar system. Far from it. They are a cosmic baby, a spectacular but transient adornment that appeared relatively recently, perhaps just tens to hundreds of millions of years ago. This revelation, born from the pure bright ice and measured mass of the rings, fundamentally rewrites Saturn's history. But if they aren't primordial, then where on Earth, or rather where in space, did they come from? What cataclysmic event, occurring long after the planets themselves had settled into their orbits, could have given birth to such a vast and magnificent structure? This question has led to some truly fascinating scientific detective work, and while we don't have a definitive answer yet, two leading hypotheses dominate the discussion, both involving immense forces and shattered celestial bodies. Let's imagine the solar system as a tranquil, well-ordered clockwork for billions of years. Saturn spins serenely, surrounded by its numerous moons, but devoid of its iconic rings. Then, something extraordinary happens. The first, and currently most favored, hypothesis is the shattered moon theory. Imagine one of Saturn's icy moons. Perhaps a medium-sized satellite, something akin to Enceladus or Tethys, but perhaps a bit larger, let's say a few hundred kilometers in diameter. For billions of years, this moon peacefully orbits Saturn. Then, something happens to shatter it. What could cause such a catastrophic event? One leading idea is a powerful, high-velocity impact from a large comet or asteroid. Our solar system is still a cosmic shooting gallery, even billions of years after its formation. Stray comets, perhaps perturbed from the distant Oort cloud or Kuiper belt, can occasionally swing into the inner solar system, sometimes on a collision course with planets or moons. If such a rogue object, moving at immense speeds, slammed into one of Saturn's icy moons, the impact would be utterly devastating. Think about the energy released by the asteroid that wiped out the dinosaurs on Earth, but scaled up to a body large enough to obliterate a small moon. The moon would be ripped apart, shattered into countless fragments of ice and rock. Now, here's where a crucial concept comes into play, the Roche limit. This is an absolutely vital piece of the puzzle, and we'll explore it in more detail in our next segment. But for now, think of it as a gravitational, no-fly zone for large, cohesive bodies. The Roche limit is the minimum distance at which a celestial body, held together only by its own gravity, can orbit another, larger body without being torn apart by tidal forces. Inside this limit, the larger body's gravity literally pulls the smaller body apart. If our shattered moon was already orbiting Sinside, Saturn's Roche limit, or if the impact propelled its fragments into this dangerous zone, then those fragments wouldn't be able to reaccrete into a new moon. Saturn's immense tidal forces, the differential gravitational pull across the fragment's body, would prevent them from clumping back together. Instead, these fragments would spread out, pulverized by subsequent collisions, and begin to orbit Saturn independently, slowly forming the flat, disc-like structure we see today. The shattered moon theory has a lot going for it. The sheer purity of the ring ice, 99.9% water, strongly suggests an icy progenitor. Most of Saturn's inner moons are predominantly icy, so a shattered icy moon fits the compositional bill perfectly. Furthermore, the total mass of the rings, as measured by Cassini, is consistent with the mass of a medium-sized moon, somewhere between Mimas and Tethys. According to sophisticated computer simulations, like those done by Robin Canup at the Southwest Research Institute, such a catastrophic impact could indeed produce a ring system that closely resembles Saturn's. But there's a variation on this theme. Perhaps the moon didn't get hit by an external object. Perhaps it was a larger, primordial icy moon, which, due to internal forces or orbital instabilities, spiraled inwards, crossing the Roche limit and being gradually torn apart by Saturn's intense tidal forces. This tidal disruption scenario also neatly explains the icy composition and the mass. It's like stretching a piece of taffy until it breaks, but on a planetary scale. Now, let's consider the second leading hypothesis, the captured icy body theory. This idea suggests that the rings weren't formed from one of Saturn's existing moons, but rather from a rogue icy body, perhaps a large comet, an ice-rich asteroid, or even a dwarf planet-sized object from the distant Kuiper belt that wandered too close to Saturn. Imagine a giant cosmic snowball, barreling through the outer solar system, perhaps disturbed by a gravitational nudge from another planet. It gets caught in Saturn's immense gravitational well. As it spirals inward, it crosses the critical threshold of the Roche limit. Just like in the shattered moon scenario, the tidal forces would begin to tear this icy visitor apart. The leading edge would be pulled harder than the trailing edge, stretching and ultimately fragmenting the body into billions of pieces. These pieces, unable to recoalesce inside the Roche limit, would then spread out to form the rings. This theory also has its merits. It explains the high-purity ice, as many comets and outer solar system objects are primarily icy. It also explains the relatively young age of the rings, as such a capture event could theoretically happen at any point in the solar system's history, rather than being restricted to the initial formation phase. According to some models, a captured icy body could potentially provide the mass needed to create the current ring system. So, which theory is correct? Scientists are still working on it. Cassini's data has certainly pushed us closer to an answer. The ring's low metallicity and high ice purity strongly favor an icy origin, ruling out many hypotheses involving rocky asteroids. The mass estimates also give us a good sense of the size of the progenitor body. The shattered moon scenario seems to have a slight edge, partly because simulations show it can more naturally produce the exact distribution of ring material and the complex structures we observe. It's also considered more statistically likely for an internal moon to be disrupted than for a precisely sized rogue icy body to be captured and torn apart in just the right way to form the rings we see. Ultimately, both theories invoke immense gravitational forces and catastrophic events. Both describe a universe that is far from static, where even settled planetary systems can experience dramatic, transformative moments. The very existence of Saturn's rings, in their current magnificent but ephemeral state, is a testament to the dynamic and sometimes violent history of our solar system. This concept of the Roche limit, this invisible line where gravity turns from a unifier into a destroyer, is so fundamental to understanding not only how Saturn's rings might have formed, but also why they exist in their current configuration, and indeed why they might eventually disappear. It's a key physical principle, and it's what we'll dive into in our next segment, unraveling the mechanics of gravity's breaking point. We've journeyed through the astounding reality of Saturn's rings, their composition, their dynamic nature, their surprisingly young age, and the catastrophic theories of their birth. In both the shattered moon and captured icy body scenarios, one fundamental concept keeps resurfacing, acting as the invisible architect of these celestial structures, the Roche limit. It's a critical idea in astrophysics, and understanding it is key to unlocking the mysteries of planetary rings, including their very existence and eventual demise. So, what exactly is the Roche limit? It sounds rather imposing, a technical term that might seem abstract, but at its heart, it's a simple, elegant demonstration of the power of gravity, specifically the power of differential gravity, or what we call tidal forces. Imagine a large celestial body, let's call it the primary, like Saturn. Now imagine a smaller celestial body, a moon or an icy rogue object, orbiting it. Both bodies have their own gravitational pull, trying to hold themselves together. But the larger body is also exerting its gravitational pull on the smaller one. Here's the trick. Gravity is not uniform across a body. The part of the smaller body closest to the primary feels a stronger gravitational pull than the part farthest away. This difference in gravitational force across the body is what we call a tidal force. Think of it this way. Hold a rubber ball in front of you. Now, imagine a giant, invisible hand pulling harder on the side of the ball closest to you and slightly less hard on the side farthest away. What happens? The ball gets stretched. It distorts. This stretching force, pulling the body apart, is the tidal force. The Roche limit, named after the French astronomer Édouard Roche, who first calculated it in the 19th century, is the theoretical distance from a primary body at which a secondary body, held together only by its own gravity, will disintegrate due to these tidal forces. Inside the Roche limit, the primary body's tidal forces become stronger than the secondary body's self-gravity. The stretching force wins, and the object is ripped apart. Let's use an analogy. Imagine you're holding a chain of magnets. If you bring a very powerful electromagnet close to one end of the chain, it will pull on that end much harder than the other end. If you get too close, the powerful electromagnet might pull the first magnet away from the rest of the chain. Now, scale that up to cosmic proportions. The exact distance of the Roche limit depends on several factors: the density of the primary body, the density of the orbiting body, and its radius. For a rigid body, the math is a bit different than for a fluid body, but the principle is the same. For Saturn, with its density and its icy moons and ring particles, its Roche limit is crucial. According to calculations, the main rings of Saturn, the A, B, and C rings, all lie comfortably inside Saturn's Roche limit. This is not a coincidence. It's the very reason they exist as rings rather than as consolidated moons. Consider the shattered moon theory we just discussed. If a moon was shattered by an impact and its fragments were located inside the Roche limit, they would never be able to reaccrete into a single, cohesive body. Saturn's immense tidal forces would constantly be pulling them apart, preventing their self-gravity from reforming a new moon. Instead, they would remain as individual particles, spread out into a disk. Similarly, if an icy comet or other body ventured too close to Saturn, crossing its Roche limit, it would be torn apart before it could collide with the planet or establish a stable orbit as a moon. Its constituent ice and rock would be shredded, dispersed, and then subjected to the same tidal forces, forming a ring system. So, the Roche limit acts as a boundary. Outside it, you find moons. It's a clear demarcation created by the differential gravitational pull of the primary body. All of Saturn's large, stable moons, like Titan, Rhea, Iapetus, orbit comfortably outside the Roche limit, where their own gravity is strong enough to hold them together against Saturn's tidal forces. But the tiny moonlets and ring particles, lying well within this boundary, are forever destined to remain individual pieces, bound by gravity to Saturn, but unable to gather into a single object. This is why, when you look at images of Saturn's rings, you don't see any large, consolidated objects within the main ring system. You see countless small particles, sometimes clumping together into temporary gravitational aggregates, like snowballs forming and breaking apart, but never forming anything stable and substantial. The largest chunks in the rings are only a few tens of meters across, small enough that their internal cohesive forces, like molecular bonds or weak gravity, can hold them together, but not large enough to overcome Saturn's tidal forces and grow into a moon. The Roche limit isn't just about formation. It also plays a role in the ongoing dynamics and the eventual disappearance of the rings. The innermost D ring, for example, is very tenuous and close to Saturn. It's so deep within the Roche limit, the particles there are highly susceptible to both tidal forces and the drag from Saturn's extended atmosphere. This contributes to the ring rain phenomenon, as these particles are easily dislodged and pulled into the planet. Furthermore, the Roche limit isn't just a fixed line, it's a zone of intense gravitational shaping. The gravitational interactions between the ring particles themselves and between the rings and Saturn's many shepherd moons, some of which skirt the very edge of the Roche limit, or even lie within it, further sculpt the rings. These tidal forces create the gaps, the ripples, the spokes, and the other intricate features we observe. They are a constant reminder of the unseen hand of gravity at work. Understanding the Roche limit helps us grasp the incredible fragility and dynamic nature of the rings. It's a constant battle between Saturn's powerful tidal forces, trying to pull everything apart, and the weaker self-gravity and cohesive forces trying to hold the particles together. The current ring system exists in a delicate equilibrium, a constant state of flux within this gravitational boundary. In essence, the Roche limit explains why the rings are rings at all, rather than a collection of small moons or a single larger moon. It explains why they can't coalesce. And critically, it underpins the theories of their formation, whether from a shattered moon or a captured icy body, as both scenarios require material to be broken up and prevented from reforming into a cohesive object within this crucial gravitational boundary. So, as we imagine a future without Saturn's rings, the Roche limit remains a silent, powerful factor. The mechanisms of ring rain, micrometeoroid impacts, and internal collisions are actively removing material. But it is the context of the Roche limit that dictates how that material behaves once it's separated. It cannot form new moons, only ever-diminishing rings. This fundamental astrophysical principle highlights the intricate dance of forces that both created and are now slowly unmaking one of the solar system's most iconic wonders. In our next segment, we'll take this knowledge and apply it to a cosmic vision. What would a ringless Saturn actually look like? We've dissected the rings, explored their icy composition, charted their surprisingly short lifespan, and understood the gravitational physics of their birth and death. We've come to terms with the scientific certainty that these majestic structures are indeed on their way out. The question now shifts from how and why to what if. What happens when the cosmic countdown finally ends? What would Saturn look like without its iconic rings? It's a difficult thought to process, isn't it? For centuries, Saturn has been defined by its rings. They are inseparable in our collective consciousness. To imagine Saturn unveiled, stripped of its celestial halo, is to imagine a profound transformation of one of our most beloved cosmic landmarks. Today, even with a small backyard telescope, Saturn's rings are a breathtaking sight. They catch the sunlight, presenting that unmistakable flattened oval shape, with the planet seemingly floating within a delicate, shining disk. This image is etched into our minds, a constant source of wonder for amateur astronomers and professional observatories alike. But in a future perhaps 100 to 300 million years from now, that iconic view would be gone. From Earth, Saturn would appear dramatically different. Instead of a majestic ring jewel, it would simply be a large, yellowish-brown orb, a gas giant with subtle bands of clouds, perhaps a hexagonal polar vortex, but nothing else. It would resemble, in many ways, a slightly larger, less colourful Jupiter, or a more distant, less distinct Uranus or Neptune. Think about the psychological impact of that. For generations, explorers, poets and scientists have gazed upon the rings. Imagine future generations looking through their telescopes, seeing only a featureless sphere. The unique character, the mystique that has drawn humanity's gaze for over 400 years, would vanish. It would be like seeing the Mona Lisa without her smile, or the pyramids without their distinct triangular forms. The very essence of what makes Saturn Saturn would be fundamentally altered. It would be a loss not just for astronomy, but for our shared cultural heritage, a poignant reminder of the transient nature of even the grandest cosmic spectacles. Now, let's zoom in, way past Earth, and imagine ourselves within the Saturnian system itself. What would it be like to witness this change from a closer perspective? Today, if you were hovering near Saturn, perhaps in orbit around one of its moons like Enceladus, the rings would dominate your view. They would stretch across the sky, a vast, flat expanse of shimmering light, sometimes casting enormous dramatic shadows across the face of Saturn itself. From certain angles they might appear as a brilliant thin line, almost disappearing edge-on. From others, a grand, awe-inspiring disk. The light from the sun would reflect off billions of icy particles, creating an ethereal glow. In a ringless future, that entire celestial panorama would be gone. The stunning views of the rings slicing across the sky would be replaced by endless blackness. The beautiful shadows the rings cast, those dark bands that stretch across Saturn's cloud tops, would vanish, replaced by a uniform, banded atmosphere. But it's not just a visual change. The rings are not simply a static adornment. They are an active component of the Saturnian system, interacting with the planet and its moons in subtle yet significant ways. For instance, the rings currently provide a small but measurable amount of light to Saturn's upper atmosphere, particularly when the planet is tilted to illuminate the rings fully. This reflected light contributes to the subtle atmospheric dynamics. Without the rings, this reflected light source would disappear, potentially altering local temperatures and atmospheric circulation patterns, though likely in a minor way compared to the sun's influence. More profoundly, the rings play a role in the constant exchange of material within the system. We've discussed ring rain as a loss mechanism for the rings. But the rings themselves are also a source of material for some of Saturn's innermost moons. For example, some of the tiny ring moons or moonlets that orbit within the rings, like Pan and Atlas, are thought to be constantly accumulating fresh ring material, growing larger and then potentially breaking apart again. Without the rings, these processes would cease. These tiny moonlets would either slowly dissipate themselves, eroded by micrometeoroid impacts, or become much more dormant, unchanging chunks of ice. Furthermore, the rings exert a gravitational influence. While their total mass is only a fraction of Saturn's, it's still substantial enough to have a measurable effect on the orbits of some of the innermost moons. With the rings gone, the intricate gravitational dance between the planet, its moons, and the rings would simplify. Some moon orbits might subtly shift, though it's unlikely to cause any catastrophic changes to the larger moons. Imagine also the perspective of an astronaut or a future deep space tourist. The primary attraction, the undisputed showstopper of the Saturnian system, would no longer be there. The breathtaking phenomenon that captivated our telescopes and our imaginations would be relegated to history books and ancient photographs. It would transform Saturn from a cosmic marvel into a giant, albeit still beautiful, gas planet. We often think of celestial bodies as eternal, unchanging entities, but Saturn's rings serve as a powerful reminder that even on cosmic scales, beauty and structure can be transient. Our solar system, far from being a static tableau, is a dynamic, constantly evolving place. Features we consider permanent are merely snapshots in time. The loss of the rings would be a poignant event, a cosmic marker. It would be a testament to the ceaseless, erosive power of space, to the constant interplay of gravity, radiation, and collisions that shape and reshape the universe over unimaginable timescales. It would force us to confront the impermanence of even the grandest spectacles. But is it truly an end-on, or is it simply a phase? Could Saturn, in the far distant future, develop new rings? Could another catastrophic event bring back this lost glory? That's a fascinating and counterintuitive question that leads us to consider the cyclical nature of cosmic structures, which we'll explore in a later segment. But first, we must acknowledge the impact this change would have on the other inhabitants of the Saturnian system, its extensive family of moons. In our next segment, we'll delve into how the disappearance of the rings might echo through the orbits and lives of Saturn's many satellites. We've imagined a ringless Saturn, a profound aesthetic transformation from our perspective on Earth and within the Saturnian system. But the rings are more than just a visual adornment. They are an active, gravitational component of Saturn's intricate family. Their disappearance wouldn't just be a cosmetic change, it would send ripples, or rather echoes, through the orbits and destinies of Saturn's extensive moon system. Saturn is a planet of incredible celestial abundance, boasting over 140 known moons. From the giant, atmosphere-shrouded Titan to tiny, tumbling moonlets mere kilometers across, this diverse collection of satellites has evolved in close gravitational harmony with Saturn and its rings. When the rings vanish, this delicate balance will inevitably shift. Let's first consider the moons that are most intimately intertwined with the rings, the inner moons and the so-called shepherd moons. These are the small, often oddly shaped satellites that orbit either within the ring system itself or very close to its edges. Think of moons like Pan, Atlas, Prometheus, and Pandora. They are essentially ring-adjacent, if not ring-dwelling. For these moons, the rings are not just a backdrop, they are a direct source of material and a constant gravitational influence. For example, Pan and Atlas, with their distinctive flying saucer or ravioli shapes, are believed to have accumulated ring material around their equators, giving them their characteristic bulging ridges. These moons are effectively sweeping up ring particles as they orbit within the Anki gap and the A ring, respectively. Without the rings, this constant accretion of fresh ice would cease. Over time, these moons would likely lose their unique shapes as micrometeoroid impacts slowly erode their equatorial bulges. They would become less distinctive, more generic icy chunks. The shepherd moons, like Prometheus and Pandora, have an even more active role. They orbit just outside the F-ring, using their gravitational pull to herd the ring particles, keeping the F-ring tightly constrained and preventing it from spreading out. They are like cosmic sheepdogs, nudging particles back into line. Without the rings, their primary function would simply disappear. Their gravitational influence would no longer be shaping and maintaining the F-ring. These moons would continue their orbits, but their most defining interaction would be gone. It's a bit like a lighthouse keeper suddenly finding the sea has vanished. The loss of the rings would also remove a subtle but widespread source of ring rain. material that currently falls not just onto Saturn, but also onto some of its inner moons. While much of the ring material falls into Saturn's atmosphere, some smaller, charged particles are also influenced by the magnetic fields of moons raining onto their surfaces. This constant dusting of fresh ice contributes to the appearance and even the geological activity of some moons. Take Enceladus, for example, famous for its south polar geysers. While primarily driven by internal heat, its interaction with the E-ring, a diffuse, outer ring fed by Enceladus's plumes, is complex. While Enceladus creates the E-ring, the presence of the main rings affects the overall particle environment. As the main rings dissipate, the broader environment of charged particles and dust would change, subtly altering the surface evolution of these inner icy worlds. What about the larger, more distant moons, like Titan, Rhea, Iapetus, or Dione? For these substantial satellites, the direct impact would be less dramatic, at least initially. They orbit far beyond the main ring system, so their gravitational dance with Saturn is the primary influence on their paths. However, the rings, despite being thin, do possess a measurable mass, which exerts its own gravitational pull. According to gravitational models, the rings contribute a small but consistent perturbation to the orbits of these moons. When the rings disappear, this perturbation will cease. This won't cause moons to suddenly spiral out of control, but it will lead to subtle, long-term shifts in their orbital parameters. Their semi-major axes, eccentricities, and inclinations might slowly adjust to the new, ringless gravitational environment. These changes would be incredibly tiny on a human timescale, but over millions of years, they would represent a measurable alteration in the dynamics of the entire Saturnian system. It's like removing a small but persistent eddy in a complex current. The overall flow will adjust. Furthermore, the rings currently act as a sort of cosmic shield, albeit a porous one, offering some protection to the inner regions of the Saturnian system from certain types of incoming cosmic debris. While not a complete barrier, their sheer mass and extent mean that some micrometeoroids and smaller objects might collide with the rings rather than directly with an inner moon. With the rings gone, the inner moons might experience a slightly increased rate of micrometeoroid bombardment, leading to a potentially faster rate of surface erosion and cratering over vast timescales. The disappearance of the rings also simplifies the overall electromagnetic environment around Saturn. The rings themselves are electrically charged and interact with Saturn's magnetic field. They influence the plasma environment, absorbing charged particles and altering the distribution of electric fields. With the rings gone, the magnetosphere would adjust to this new reality, potentially affecting phenomena like Saturn's aurorae or the overall flow of charged particles around the planet. In essence, the rings are not just aesthetically pleasing, they are an integral, dynamic part of the Saturnian system. Their demise represents a systemic change, not just a cosmetic one. The inner moons, which have evolved in such close proximity and interaction with the rings, will undoubtedly be the most affected, losing their sculpting forces and sources of accretion. The larger moons will experience more subtle, long-term orbital adjustments. The echoes of the rings' disappearance will reverberate throughout the Saturnian system, a quiet testament to the interconnectedness of celestial bodies. It's a powerful reminder that planetary systems are not static collections of objects, but complex, evolving ecosystems where every component plays a role. As we contemplate this ringless future, it leads us to a broader question. How unique is Saturn's current magnificence? Are rings a common feature in the cosmos, or is Saturn's system truly an outlier? That's what we'll explore in our next segment, as we compare Saturn's rings to those found elsewhere in our solar system. We've delved deep into Saturn's magnificent rings, unraveling their composition, their dynamic life, and their inevitable demise. We've even imagined a ringless future for the iconic gas giant. But all of this discussion has revolved around Saturn, almost as if it's the only planet with rings. Is Saturn truly unique in its ringed glory, or are there other cosmic hula hoopers out there? And if so, why is Saturn's ring system so dramatically different, so much more prominent and spectacular than any other in our solar system? It might surprise some to learn that Saturn is not, in fact, the only planet in our solar system with rings. Jupiter, Uranus, and Neptune all possess their own ring systems. However, a crucial distinction immediately becomes apparent. You've probably never seen a picture of Jupiter's rings on a textbook cover, or Uranus's rings on a poster. There's a very good reason for that. Let's take a comparative tour, starting with Jupiter. After Saturn, Jupiter is the solar system's largest planet, a true behemoth. So, you might expect it to have equally impressive rings. But when the Voyager 1 spacecraft flew past Jupiter in 1979, it discovered a ring system that was, frankly, a bit of a disappointment to those expecting a Saturnian spectacle. Jupiter's rings are incredibly faint, diffuse, and composed primarily of tiny, dark, dusty particles. They are barely visible even in direct sunlight, and only appeared in Voyager's images after careful processing. According to observations from Galileo and Juno spacecraft, these rings are largely composed of pulverized dust kicked up from Jupiter's small inner moons like Metis, Adraste, and Amalthea by micrometeoroid impacts. These tiny dark particles, rich in silicates, don't reflect much light, making them difficult to spot. They also don't last long, constantly falling into Jupiter's atmosphere or being replenished by new impacts. Jupiter's ring system is essentially a transient, dusty haze, a mere whisper compared to Saturn's roaring symphony. Next, we journey to the ice giants, Uranus and Neptune. These planets also boast rings, discovered by Voyager 2 in the 1980s. Uranus, famously tilted on its side, has a system of 13 known rings, which were actually first detected from Earth in 1977 during a stellar occultation, when the planet passed in front of a distant star and the rings briefly dimmed the starlight. Uranus's rings are also quite dark and narrow, composed of mostly rocky, carbon-rich material rather than bright ice. They are much more substantial than Jupiter's dusty wisps, with some rings being several kilometers wide. However, they are still nowhere near as bright, broad, or massive as Saturn's. They have sharp, well-defined edges, likely sculpted by tiny, unseen shepherd moons. According to detailed observations, the particles in Uranus's rings range from dust to small boulders, but again, they lack the sheer volume of pristine ice that defines Saturn's rings. Neptune, the outermost gas giant, also possesses faint, narrow rings. Its most famous feature is the arcs within its outermost ring, which are denser clumps of material that don't seem to spread out evenly. This unique characteristic is thought to be due to the gravitational influence of a tiny inner moon, Galatea. Like Uranus, Neptune's rings are dark, dusty, and likely composed of similar rocky, carbonaceous material. They are also quite tenuous, almost like wisps, rather than the dense, broad bands of Saturn. So, the question remains, why is Saturn the undisputed ring king? What makes its rings so incredibly prominent, massive, pure, and diverse in their structure compared to its siblings? There are several contributing factors, and they bring us back to the concepts we've already explored. 1. Composition. This is arguably the biggest differentiator. Saturn's rings are almost 99.9% pure water ice. Ice is incredibly reflective, scattering sunlight brilliantly. Jupiter's, Uranus's, and Neptune's rings are predominantly dark, rocky, carbon-rich material. They absorb light rather than reflecting it, making them inherently much fainter and harder to see. This difference in composition also goes back to our discussion of ring age. Dirty, rocky rings are expected for older systems, constantly accumulating space dust. 2. Mass and particle size. Saturn's rings are enormously massive. According to Cassini data, their total mass is estimated to be roughly equivalent to a small icy moon like Mimas or Tethys. The other planets' rings are far less massive, sometimes by orders of magnitude. This mass, combined with a wide range of particle sizes from microns to mountains, contributes to their density and visibility. The sheer volume of material in Saturn's rings simply dwarfs that of the other planets. 3. Youthful age. This is a crucial, overarching reason. As we discussed, Saturn's rings are relatively young, perhaps only tens to hundreds of millions of years old. This youth means they haven't had billions of years to accumulate dark, contaminating space dust, hence their pristine, icy appearance. The rings of Jupiter, Uranus, and Neptune are generally believed to be much older, likely primordial, formed alongside their planets. Over those billions of years, they've accumulated far more darker material, losing their initial brightness. 4. Progenitor object. The leading theories for Saturn's rings involve the catastrophic disruption of a relatively large, ice-like moon, or captured icy body. This would have supplied an enormous amount of pure water ice. Particular sepsin and wrong passons and gaps and gapst, and a Saturn's role in creating the sharp edge gapsons that gaps to patterns that give Saturn's role in creating the sharp edges, which then happen to Saturn's rings their diverse and stunning structure. The other gas-giants one passons that gapped configurations are rings formed from less reflective materials or simply smaller, less dramatic event involving a substantial body of pure ice, which then happen to shatter and disperse within its Roche limit, creating a vast and disperse within its Roche limit, creating a vast phenomenon. It be gas-giants really inet to net, or rings formed from less extrements command, or rings the crumb spectacle, septims that yield. We've journeyed through the astounding science of Saturn's rings, from their shimmering present to their inevitable, measured disappearance. We understand how they're fading, why they're so pristine, and when they likely formed. We've even considered the profound impact of their loss on both our view of Saturn and its surrounding moon system. But the word end can be deceptively simple. When we say the rings are disappearing, does that mean a permanent final conclusion to Saturn's ringed glory? Or is it possible that this disappearance is merely a phase, a chapter in a much grander cyclical story of cosmic creation and destruction? Could Saturn, in the unimaginably distant future, regain its halo? This question pushes us beyond the immediate data and into the realm of astrophysical speculation and long-term cosmic evolution. It forces us to consider the universe not as a static collection of objects, but as a constantly churning, recycling system. Think about celestial objects like stars. They are born from clouds of gas and dust, live for millions or billions of years, and then die, sometimes in spectacular supernovae, returning their material to the cosmos to form new stars and planets. This is a cycle of cosmic rebirth. Could planetary rings follow a similar pattern? According to current scientific understanding, the formation of planetary rings is almost always linked to a catastrophic event, a moon shattered by an impact, or a body torn apart by tidal forces upon crossing the Roche limit. These events are not everyday occurrences, but they are also not once-in-a-solar system phenomena. Our solar system is a dynamic place, still peppered with comets and asteroids, still subject to gravitational nudges and perturbations. Could another one of Saturn's existing icy moons, in the very distant future, suffer a devastating impact? Or could its orbit gradually destabilize, drawing it inward across the Roche limit, where it would be ripped apart? Absolutely. It's entirely within the realm of astrophysical possibility. Imagine a scenario. Millions of years after Saturn's current rings have mostly dissipated into the planet, a medium-sized icy moon, perhaps one that currently orbits farther out, experiences a significant orbital perturbation, a gravitational dance with another moon, or a subtle nudge from a passing rogue object, might slowly, imperceptibly alter its path. Over vast stretches of time, this moon might eventually drift inwards, inexorably drawn towards Saturn. As it crosses the Roche limit, it would succumb to the planet's immense tidal forces, just as the progenitor of the current rings presumably did. This new, shattered moon would then provide a fresh supply of icy particles, potentially birthing a new generation of rings. It's a compelling idea, a cosmic recycling program for planetary rings. The material from the old rings falls into the planet, becoming part of Saturn's atmosphere. Then, new material from a moon is released to form fresh rings. This cyclical process implies that Saturn might be a ringed planet, off and on throughout its billions of years of existence, rather than having just one glorious but ultimately terminal ring phase. What evidence supports this idea beyond theoretical possibility? When we look at the other gas giants, their rings are generally considered much older, primordial. But they are also dark and dusty, suggesting a different, perhaps less spectacular origin, or simply a very long period of contamination. However, the very fact that Saturn's rings are so young is a strong hint that they might not be a one-off event. If they had formed 4.5 billion years ago and simply persisted, then their youth wouldn't be such a striking discovery. Their recent appearance, however, suggests that ring formation can happen any time during a planet's life. Think about the rings of Uranus and Neptune. While faint, they are still there, millions of years after their formation. This suggests that once formed, even if made of less reflective material, ring systems can persist for very long durations, even billions of years. So, Saturn's current rings are unique in their youthful radiance, not necessarily in the fact that they are rings at all. This opens the door to the idea that a new, equally magnificent set of rings could form later, if the right icy raw material became available in the right place at the right time. This cyclical view of rings also aligns with a broader understanding of cosmic evolution. Galaxies collide and merge, stars are born, die, and rebirth, planets migrate in their orbits. Nothing in the universe is truly static or permanent on the longest timescales. So why should planetary rings be an exception? This doesn't mean Saturn will always have rings, or that new rings would be identical to the ones we see today. The specific mass, composition, and orbital dynamics of the progenitor body would dictate the nature of any future ring system. It might be less massive, or more rocky, or arranged differently. But the set potential for ring formation, the availability of icy moons, and the inexorable power of tidal forces and impacts mean that Saturn's glory could, in theory, be renewed. This idea of a cosmic cycle provides a fascinating, somewhat comforting perspective. The end of the rings isn't a final death, but perhaps a transition, a shedding of old material in preparation for a potential future rebirth. It transforms Saturn from a planet whose finest moment is passing into a celestial stage where magnificent, albeit transient, dramas play out over eons. This understanding also broadens our appreciation for what we are witnessing right now. If rings are fleeting, temporary phenomena, then seeing Saturn's rings today is akin to witnessing a particularly rare and beautiful bloom in a cosmic garden. We are